So this is a definition of power and energy over a finite time interval. But sometimes we may be interested in the energy and the power associated with infinite time. So similarly, we can define the infinite time energy and power as follows, which we call the infinite time period the total energy. So we have the total energy for continuous time, E infinity, is defined as, which means this this integration will be from minus infinity to infinity, which means its limit t goes to infinity, and the integrate from minus t to t. The magnitude square. And then for discrete time signal, we have the total energy is defined as still we have n goes to infinity, and we sum have minus 1 to so this equals to integral from minus infinity to infinity. And this is equivalent to say we sum from infinity, negative infinity to infinity. Okay. And after we have the total energy, and we can see that, so since we have an integration sum in infinite time steps, so there will exist a convergence issue, which means, so sometimes this integration is not, it does not converge. Like if we have a positive value in xt for all t, then this integration goes to infinity as well. Similarly, so if for discrete time signals, if we have non-negative or positive values for all n, then this sum is also goes to infinity. So if this situation happens, then we have infinite energy, right? And otherwise, if they converge, we have finite. We have finite energy for this signal. So, for example, if this xn or xt equal to 1 for all n or all t, we have infinite energy. And if our signal is only over a finite period of time, then this sum will be guaranteed to be finite. So let's take one example to clearly see this fact. Xt equal to 4 minus square when t is less to 2 and 0 for else. And we can try to calculate the energy, the total energy of this signal as an exercise. So please do that. And then I will show you. We'll work on this problem together. Okay, so energy, total energy for this signal as a definition. So it's from infinity to infinity. And this signal square. Which equals to 16 minus 8t squared plus t fourth t to the 4 dt. And since all the other, it only has possibly non-zero values between -2 to 2, and the other part are zeros, so which is equivalent to say we have integration from -2 to 2 only on this signal, because all the other integrations will be on the integration on the other part will be 0. So you can see this equals to 16t minus 3 e over 3t squared t cubed and fifth t to the 5 and value at minus 2 and 2. So you can substitute into to this equation minus this equation substitute into minus 2. And then we can get the energy. Factor of over 50 to get the right answer. So since we have, so we defined the power, which is the average energy over a specific time period. And we can also define the power over infinite interval. So we have P infinity defined as when t equals to infinity, 1 to t in the total energy. This is for continuous term, and for discrete term, so we have P infinity equals to n goes to infinity, 2n plus 1. And as I said, if we have this xn equals 1 for all n, for any integer n, what is the average power of this signal? Can we calculate that? So we can see it will be limit n goes to infinity, 0 plus 1 use the definition here. So it will be -1 to n x1 squared. So this will be 1. And this sum will be so from -n to n, and every value is 1. So it will be 2n plus 1. So this is equal to 1. Makes sense? Because you have a 1 at each point, then the average energy is also 1. But we note that the total energy of this signal is infinite. So we can see in general, so if a signal has a finite energy, and so if its energy is finite, and when we consider the infinite interval, so its P infinity will be what? Since it's a finite here, and this n goes to, or t goes to infinity, so we can see P infinity goes to 0. So we say it has 0 average power. So now we can have a look at some important classes of signals. So, so this is called the energy signal, and then this is with also energy signal means it has finite energy, and power signal, if it has finite power. But so you know, this means the energy, average energy is 0. And so sometimes for this signal, the total energy is infinite. So a signal cannot be, so if this happens, yeah, the energy will be infinite. And a signal cannot be both energy signal and power signal because of this relationship. So if it has finite energy, it must have 0 average power. So this is the relationship, and similarly we have if P energy is finite, and E, the total energy will be infinite. Okay. So now we just introduce the signal energy and the power. So next we will continue discussing the transformations of the independent variables. So since signal, sometimes the systems, some systems can deal with some, do some transformation of the independent variables. So like the delay registers can delay your signals. So which means if we have a signal st, then after the register, so it will be like st minus t0. means delete the signal for some time period. So this is called time shifting. So we use example to see the time shifting. So we have, suppose we have xn, we use discrete signal. And when this signal, like, suppose this signal has okay, 0, 2, -1, -2. And we want to shift this signal by n0 time steps. So for example, we can let n0 equal to 2 here. So after this time shifting, you can see this is xn, x2, okay. And so when n equals to 2, after the shifting, n equals to 4. Right? The 4 minus 2 is 2. So we shift this signal here. And similarly, 1 here. 3, 1, 3, 2. This one, 0. So it shifted this signal with the same shape. It is a shifted version of xn. Okay, and similarly for the continuous time, and we also have shifted version t minus t0. So t0 is a time period. So similarly, so if we have a signal, this triangular as a signal from t0 to 1, and if you have shifted by t0, then the signal will be with the same shape. But with the time indices shifted. Okay. Another transformation on the independent variable is called the time reverse. So as you can distinguish from the term of this transformation, it reverses the time. So if you have signal xt, and after the time reversal, what it will be? So it And similarly, if we have lec1, and then we have x minus 1. So still use these two examples here. So if you have this signal, and after the time reversal, it will be 0 keeps the same position, and now 1 becomes -1. So you flip the two sides. This will be 1, 0. This will be 2. This will be -1. This 2. Okay? Similarly for this signal, continuous time signals, so reversal will be like this. 0, -1. Okay? And another transformation we will talk about is time scaling.
It's 6 o'clock.
So which means it will scale the time index here. And one will be like stretched version of the signal, and the other will be the compressed version or shrunk version of the signal. So we can see if we have x1 or xt, and we can have a scale alpha on the time variable. And we have x alpha n and x alpha t respectively. And so we first look at the continuous time, because it's easier to understand. So if we have like this signal, and when we have a alpha, so it depends on, of course, if alpha equal to 1, it keeps the same. And if alpha is negative, then we first flip and then do the same thing. So we assume that alpha greater than or equal to 0, greater than or equal to 0, and then we will see the effect of the signal. So if you have, and then we can, alpha have, could be less than 1 or greater than 1. So if it's less than 1, so which means the new time step will be a, if it's less than 1, which means the new signal will be, sorry, this one, alpha t. So it will be sometime here when t is equal to t1. So we have t1 here, but the value is some value here, alpha t1. And then the original T1 will be reached as T1 over alpha. So since alpha is less than 1, so this is greater than T1. So you can see we stretch the signal. And reversely, if alpha is greater than 1, this is the new signal at t1, it's already 0 because alpha is greater than 1. It will take values after t1 here. So it's already 0. And the t1 here is reached by t1 over alpha. But this time, this will be less than t1. This will be 0. The signal will be this way. So shrink the signal. Okay. Now, if we consider both positive and negative alphas, and you can see, as I said, if alpha is negative, so you will first flip the signal and then do the same trick again. So, in general, we have the stretching occurs if this is less than 1. And if the cardinality of alpha is greater than 1, then the shrink occurs. Okay, now we just discussed the continuous term, so that's easier. But for discrete term, and if we have some, since we said that for discrete term we don't have non-integer positions. So if alpha equal to half, then we will have the new signal will be x n over 2. But when n equal to 1, what value, which value should we take? Since x half is not defined. So that's why we will avoid discrete time stretching for this time. But we would, if we have time, we can talk about what should we do when this solution happens. So now we only consider the shrinking, which means alpha is greater than 1 for discrete time. And in that case, it's guaranteed that we can, if alpha is greater than 1, and of course alpha also need to be integer, and we can always have some shrinking version of the discrete time signals. And a general form of the transformation of the independent variable. So here we won't have with a scale to the time variable, but we could also have some other constant to do more shift. So we cannot we can have both shifting and transformation. So we have xn, now we can have x alpha n plus beta. So for example, we use this example. We can have x2n plus 1. Okay, what is that? So when n equal to 0, it's x1. And n equal to 1 is x3. Okay. 0, 1. x1. And when n equals to minus 1, it is x1 again. Sorry, it's minus 1. It is can see it's firstly, so we shifted this signal by 1, right? Shifted by 1, and then shrink by the factor of 2. So it's different. It's different with you shrink first and then do the scale. Because if you shrink first, which means you have x2n first, and then when you shift, you will have 2 and minus 1. It's different, or plus 1. Left shift. So then it will be x2 and plus 2. So it's different. So you must shift first and then you will do the shrinking. So we can have an example to see the difference between these two. You can work on both. For a continuous time signal, we have xt equal to 0 minus 1 t squared 1 0 t minus 1 0 to 1. You can plot this signal and then do the, let's do the x minus half t plus 1. So this way you can left shift by 1 first and then do this scale. And also since it's equivalent to t minus 2, right? Minus 2, so you can shift it by 2 first and then do the whole scaling. So you can try both ways, see if you can get the same signal.